The final chapter of our universe is not a single story. Heat death, the big crunch, the big rip, these are just the opening acts in a cosmic drama with 25 possible endings. By the end of this journey, you will possess a complete map of every way our cosmos could meet its demise. We will venture into futures where the very fabric of space tears itself apart, and others where reality itself is rewritten by a single bubble. What does it mean for everything to end, not with a bang, but with a frozen, silent whisper? Which of these incredible fates feels the most real to you? Our journey begins with the most accepted and perhaps the most haunting forecast for the cosmos. It is known as heat death, or the big freeze. This is not a violent end, but a slow, inevitable fade into nothingness. The driving force behind it is a concept called entropy. In simple terms, entropy is a measure of disorder, and a fundamental law of our universe states that it always increases. Think of a hot cup of coffee left on a table. It does not stay hot forever. It cools down, its heat spreading out into the room until everything is the same lukewarm temperature. The energy is still there, but it is now useless. It cannot be used to do any work. The universe is doing the exact same thing, on a scale so vast it defies comprehension. Right now, we live in a cosmos rich with difference. We have blazing stars and the cold darkness between them. We have dense galaxies and empty voids. These differences, these energy gradients, are what power everything. They allow stars to shine, planets to form, and life to emerge. But entropy is the great leveler. Over trillions upon trillions of years, every star will eventually exhaust its nuclear fuel. Galaxies will dim, their lights winking out one by one. The last flickers of starlight will vanish, leaving behind a graveyard of dead stars, neutron stars, and black holes. But even these remnants are not permanent. Through a process predicted by Stephen Hawking, black holes themselves slowly evaporate, leaking away their mass over unimaginable eons until they, too, pop out of existence. When the last black hole has faded, what remains is a universe that is almost perfectly uniform. A thin, cold soup of fundamental particles and radiation, spread so thinly that no two particles may ever meet again. The temperature everywhere approaches absolute zero, the point where all motion ceases. This is the essence of heat death. No more energy flows, because there is nowhere for it to flow to. Everywhere is the same. No work can be done. No new structures can form. Time itself may become meaningless, as there are no events to mark its passage. The universe reaches a state of maximum entropy, a final, eternal equilibrium. It is not an explosion into oblivion, but a whisper that grows fainter and fainter until only silence remains, a profound cosmic stillness that lasts forever. This is the fate that current physics points toward, a slow fade into a dark and frozen eternity. Yet, as we will see, our universe may have other, far more dramatic endings in store. But heat death is not the only story our universe might tell. There exists a dramatic, almost poetic alternative, a mirror image of our fiery beginning. This is the Big Crunch. What if the grand expansion we observe today is not forever? What if, instead of fading into cold silence, the cosmos decides to turn around and come home? This scenario hinges on a cosmic tug-of-war between two fundamental forces. On one side, we have the initial momentum of the Big Bang, which has been driving galaxies apart for billions of years. On the other, we have the relentless pull of gravity, the invisible glue that tries to hold everything together. The fate of the universe depends on which force ultimately wins. For a big crunch to happen, the total density of all matter and energy in the cosmos must be above a critical threshold. Think of it like tossing a ball into the air. If you throw it with enough speed, it escapes Earth's gravity and flies into space. But if your throw is too weak, Gravity pulls it back down. In the Big Crunch scenario, the universe's initial throw, the Big Bang, was not powerful enough for a permanent escape. The collective gravity of every star, every galaxy, every speck of dark matter acts as a cosmic anchor. After eons of expansion, this gravity would finally apply the brakes. The universe would slow, then stop, and then begin to contract. Picture the last 13.8 billion years of cosmic history, but played in reverse. First, distant galaxies would halt their retreat. Then, they would begin to approach one another, slowly at first, then with gathering speed. The night sky, which has been growing darker and emptier, would start to fill up again. Constellations would blur and merge as galaxies rushed together in a catastrophic traffic jam of stars. As space itself shrinks, the temperature of the cosmic background radiation, the fading echo of the Big Bang, would begin to rise. The cold of the deep void would be replaced by a pervasive, growing warmth. This warmth would turn to heat, then to an unbearable furnace glow as the universe compresses. Planets would be boiled away, stars would be torn from their orbits and smashed together, triggering titanic explosions. Eventually, all matter would be packed into an inferno of unimaginable density and temperature, a cosmic pressure cooker where atoms, then atomic nuclei, then the very particles that make them up, are crushed out of existence. Everything, all of space, time, and matter, would be driven back into a single point of infinite density, a singularity. It is the Big Bang in reverse, a final, all-encompassing collapse. This idea leads to a profound and haunting possibility. What if our Big Bang was not the absolute beginning, but merely one beat in an endless cosmic heart? If the universe can collapse into a singularity, could that singularity then rebound, sparking a new Big Bang? This is the concept of the Big Bounce, a cyclical universe of endless expansion and contraction, of death and rebirth on the grandest possible scale. Each cycle could last trillions of years, with physics potentially resetting each time, giving rise to entirely new laws and constants. Our entire cosmic epoch, from the first flash of light to the last collapsing star, would be just one chapter in an infinite book. The Big Crunch offers a very different kind of finale, one defined not by silent emptiness, but by a fiery, all-consuming reunion. Yet, our exploration of cosmic endings has only just begun, and the next possibility is perhaps the most violently abrupt of them all. The Big Crunch presents a universe that ultimately pulls itself back together. But our cosmos may be destined for a fate that is its exact opposite, a finale of ultimate disintegration. This is the Big Rip, and it is driven by the most mysterious force we have ever detected: dark energy. We know dark energy is causing the expansion of the universe to accelerate, pushing galaxies apart at ever-increasing speeds. But what if this force does not remain constant? What if it grows stronger over time? This terrifying possibility is known as phantom dark energy. In this scenario, the repulsive push of dark energy does not just continue, it intensifies, becoming exponentially more powerful with every passing moment. The fabric of space itself would begin to stretch at an accelerating rate, not just between galaxies, but everywhere. The first casualties would be the largest structures bound by the weakest gravity. Tens of billions of years from now, the gentle tug that holds clusters of galaxies together would be the first to fail. These immense cities of stars, which have remained gravitationally linked for eons, would be violently wrenched apart. Their member galaxies would be flung into the ever-widening void, forever isolated. Next, the bonds within individual galaxies would snap. The Milky Way, Andromeda, and all their stellar neighbors would be shredded. Stars would be torn from their orbits, sent careening into the darkness like sparks from a colossal explosion. The familiar spiral arms and glowing cores of galaxies would dissolve into a chaotic spray of lonely suns. But the horror would not stop there. As phantom energy's grip tightened, it would target smaller and smaller structures. Within a solar system, the sun's gravity would be the next to be overwhelmed. Planets would be ripped from their orbits. Earth would be flung into the endless night, a frozen, solitary rock adrift in an impossibly vast emptiness. Then, the force would turn inward. The gravity holding a planet together would fail. Mountains, continents, the very ground beneath your feet would be pulled apart, the planet exploding into a cloud of dust and rubble. And still, the rip continues. It would attack the forces that hold matter itself together. The electromagnetic force that binds atoms into molecules would be broken. Every object, every piece of dust, would disintegrate into a haze of individual atoms. Finally, in the last fleeting moments, the rip would target the fabric of reality at the smallest scales. The strong nuclear force, the immensely powerful glue that holds the nuclei of atoms together, would be defeated. Protons and neutrons would be torn asunder. Then, even the particles that make up protons and neutrons, quarks, would be ripped apart from one another. In a finite, calculable moment, every single bit of matter in the universe would be shredded down to its most fundamental, disconnected pieces. The timeline for this apocalypse is shockingly brief on a cosmic scale. Some models suggest the entire process, from the tearing of galaxy clusters to the dissolution of atoms, could occur within a few tens of billions of years. Compared to the trillions of years of the heat-death scenario, the Big Rip is a sudden, violent, and total demolition of everything that exists. It is not a slow fade or a fiery collapse, but an unraveling so complete that it leaves no structure, no molecule, no particle intact. The universe would end not with a whimper or a bang, but with a deafening, infinite tear. The Big Rip tears reality apart from the outside in, but there is a threat that could rewrite the universe from within. This is vacuum-decay, a scenario born from the unsettling idea that our entire cosmos is built on unstable ground. Physicists describe the fundamental fields that fill all of space as existing in a state like a valley. Our universe sits comfortably in what is called a false vacuum. It is stable for now, like a ball resting in a small dip on a mountainside. It feels solid and permanent, but there exists a much deeper valley far below, a state of true vacuum with far lower energy. The terrifying possibility is that through a random quantum event, a tiny bubble of this true vacuum could spontaneously form anywhere, at any time. This would be a process called quantum tunneling, where reality cheats, skipping over the mountain between the valleys in an instant. Once this bubble of true vacuum appears, the rules change catastrophically. The laws of physics inside it would be different, and this new state is infinitely more stable. The bubble would then expand in all directions at the speed of light, its wall a sphere of ultimate transformation. From our perspective, there would be no warning. One moment, the universe is normal. The next, a wall of pure rewriting approaches, moving so fast that you could not see it coming. It would be the last thing you never see. As the bubble wall passes through a region of space, it permanently alters the very fabric of reality. The constants that govern our existence, like the strength of gravity or the charge of an electron, would be reset to new values. The delicate balance that allows atoms to form, stars to burn, and life to exist would be erased. Chemistry, as we know it, would cease. The structure of matter itself would dissolve. Everything, from the largest galaxy to the smallest DNA strand, would be unmade and reorganized according to new, alien laws that are almost certainly incompatible with any form of life or complex structure we can imagine. The universe would continue, but it would be a different universe, one where our history, our physics, and our very memory are not just gone, but were never possible to begin with. The most haunting aspect is the randomness. This bubble could have formed in the distant past, and its light-speed wall could be on its way to us right now, or it could trigger 1 billion years from now in a galaxy far away. or it could happen in the room around you in the very next second. Vacuum decay presents an end that is not just about destruction, but about erasure and replacement, a silent reboot of reality with no chance of survival. It suggests our cosmic home is not a permanent fortress, but a temporary shelter, and the ground beneath all things could give way without a sound. The silent, random threat of vacuum decay has another name in the corridors of theoretical physics, one that sounds deceptively gentle, the Big Slurp. It captures the idea of our universe being suddenly consumed by a new, lower energy state, as if reality itself were taking one final, irrevocable sip. While this bubble could form spontaneously from quantum fluctuations, physicists like Sidney Coleman explored whether we could, in theory, trigger it ourselves. The unsettling answer is maybe. The immense energy is concentrated in collisions at particle accelerators like the Large Hadron Collider create conditions for a split second that have not existed since the universe's first moments. In these microscopic fireballs, the Higgs field, which gives particles their mass, could be jolted. The fear was that such an event could act like a spark, nudging the field over the metaphorical mountain and into that deeper, true vacuum valley, nucleating the deadly bubble. The same terrifying possibility exists from natural cosmic events. An ultra-high-energy cosmic ray, a subatomic particle accelerated to nearly the speed of light by a distant black hole or quasar, could slam into our atmosphere with far more energy than any human-made machine. That collision could, in principle, provide the necessary kick. Now, it is crucial to understand the consensus is that this is spectacularly, astronomically unlikely. The energies needed are probably far beyond what we can ever achieve, and the universe has been conducting far more violent experiments for billions of years without slurping itself. But the mere theoretical possibility highlights a profound cosmological implication. The stability of our universe is not guaranteed. It is a question of measurement. The mass of the Higgs boson, discovered in 2012, suggests our cosmic vacuum might indeed be metastable, that we are living in that precarious mountain dip. Dismantle every object not already consumed by a black hole. Planets, asteroid belts, the frozen corpses of stars, all of it would gradually fade into nothingness. The universe would be left in a profoundly simpler state, a cosmos containing only a sparse sea of leptons like electrons and positrons, photons of light, and the looming patient black holes. This is not a dramatic climax, but the universe quietly forgetting what matter even was, setting the stage for the next, even more barren chapter in the epic timeline of heat death. Black holes become the final architects of a dark cosmos. After the last proton has faded and the final embers of matter have cooled, these gravitational titans inherit the universe. This is the black hole era, a dominion of pure gravity stretching across timescales so vast they defy human comprehension. Picture a space that is almost perfectly black, an endless void. Yet here and there, faint points of light persist. These are not stars, but black holes, glowing with a ghostly radiation. They are not sucking in light, but slowly leaking it away. This is Hawking radiation, a quantum whisper at the event horizon. Pairs of virtual particles, constantly popping in and out of existence, can be separated by the black hole's immense gravity. One falls in, the other escapes, carrying away a tiny bit of the black hole's mass. It is an excruciatingly slow drip. A black hole with the mass of our sun would take about 10 to the 67 years to evaporate completely. That is a 1 followed by 67 zeros, a number so large it is longer than the current age of the universe by many orders of magnitude. For the supermassive black holes at the centers of galaxies like Sagittarius A star in the Milky Way, the timeline is almost ludicrous. We are talking 10 to the 100 years, a Google years. At this point, time itself loses meaning. measured only by the imperceptible dimming of these last beacons. Some futurists like Isaac Asimov have speculated that this era could host the last possible civilizations. Any intelligence surviving the eons would have long since abandoned biology, existing as patterns of information. They might find a way to orbit these black holes, not to avoid being pulled in, but to harvest the minuscule energy of their hawking radiation. It would be the ultimate act of cosmic scavenging, living off the last banked heat of a dying universe. These civilizations would huddle around the fading glow, their thoughts and computations slowing as the energy output dwindles. The black hole era is not static, however. It has a dramatic, explosive finale. As a black hole nears the end of its evaporation, the process accelerates. The smaller it gets, the hotter it glows and the faster it loses mass. In its final seconds, a stellar mass black hole would release a burst of energy equivalent to millions of hydrogen bombs. A final, brilliant flash in the eternal dark. One by one, across the cosmos over eons. Beyond counting, these last structures will pop like bubbles. Each flash signals the end of a gravitational empire that lasted longer than all the ages of stars. And when the last black hole vanishes, the universe enters a new, even more barren phase, a realm of near total emptiness where the very concept of structure becomes a forgotten memory. The end of all things may be written in its very first moments. The theory of cosmic inflation describes a fraction of a second after the Big Bang, when space itself expanded faster than light, smoothing and stretching the infant universe. But a profound question remains. Did inflation truly end everywhere, or did it just stop in our local neighborhood? Imagine an endless ocean of space that is still inflating, eternally stretching. Within this frothing sea, pockets like ours occasionally stop inflating, crystallizing into stable bubbles with their own laws of physics. We live inside one such bubble, our entire observable universe. This is the landscape of eternal inflation, a multiverse in constant, chaotic birth. The danger lies in the walls. Each bubble universe expands at the speed of light within the inflating background. What happens if another bubble, born from a different set of initial conditions, is on a collision course with ours? The moment of contact would be a cataclysm beyond any supernova. The boundary between our bubble and the invading one would be a wall of pure energy and rearranged fundamental forces, a shockwave of ultimate density sweeping through the cosmos. From our perspective, it would appear without warning, a sphere of annihilation expanding at light speed. As it passed, the very constants of nature would be rewritten. The forces that hold your atoms together would change or cease to function. Galaxies, stars, planets, and life would not be burned or crushed, but unmade, transformed into something alien according to new, foreign physics. It would be less like an explosion and more like a wave of erasure, turning the page from our universe's story to another's in an instant. Alternatively, even without a collision, the stability of our bubble is not guaranteed. The local laws we depend on, the strength of gravity, the masses of particles, might only be a temporary arrangement within our pocket of the multiverse. A quantum shift could cause our own bubble wall to begin moving, initiating a phase transition that consumes us from within, not unlike the Big Slurp, but triggered by our bubble's inherent instability. This idea ties the ultimate fate of everything directly to its origin. We are not just a universe evolving in isolation, but a single clearing in an infinite, inflating forest, forever vulnerable to the growth of the trees around us. Our entire cosmic history, from the first stars to the rise of consciousness, could be rendered a fleeting, local phenomenon, wiped away by a collision with a neighbor we never knew existed. Yet the singularity of a big crunch may not be a final wall. There is a possibility that the universe could rebound, turning its ultimate collapse into a new beginning. This is the Big Bounce, a vision of cosmic renewal that offers a profound alternative to permanent endings. In the classical view of gravity, a collapsing universe would be crushed into an infinitely dense point, a dead end from which nothing could return. But when we approach such extremes, quantum gravity must take over, and its rules are different. Theories like loop quantum cosmology suggest that gravity becomes repulsive at incredibly high densities, acting like a cosmic trampoline. Instead of hitting a wall of infinite density, the collapsing universe would encounter a quantum bridge. At a scale a trillion times smaller than an atom, the very geometry of space would resist further compression. The collapse would halt, reverse, and explode outward in a new Big Bang. In this model, there's no true beginning or end, only an endless series of cycles, a cosmic heartbeat. Each cycle, or aeon, could last for trillions of years, encompassing everything from a hot, dense birth to a cold, dark death, only to be reborn again. This cyclical nature raises a tantalizing question. If the universe bounces, does anything survive the transition? Is each cycle a completely blank slate with new laws of physics and constants, or does some faint echo of the previous universe linger? Some theorists propose that while stars, galaxies, and all structures are obliterated and remade, quantum information might be preserved. The fundamental blueprint of reality, in some scrambled form, could carry over, meaning each new universe is not entirely independent, but a transformation of what came before. Perhaps even the numerical values of the constants, like the strength of gravity or the mass of an electron, could be subtly different in each new cycle, leading to universes that are similar but never quite identical to our own. The Big Bounce transforms the narrative from a linear tragedy into an epic without finality. Our universe becomes one chapter in an infinite book, its heat death or big crunch merely the turning of a page. This idea offers a strange kind of cosmological optimism where even in total collapse, the seeds of a new reality are already waiting, but a universe that stops is not necessarily a universe that is saved. Another theoretical possibility emerges from the shifting nature of dark energy itself, a scenario known as the Big Break, or sometimes the Big Snap. This is not a gentle deceleration. It is a cosmic emergency stop so violent it could tear reality from its hinges. We have seen how phantom dark energy could accelerate expansion into a big rip. But what if dark energy evolves in the opposite direction? What if it transforms into a force of immense negative pressure, a cosmic glue so potent it slams the brakes on the universe's flight? In this model, the expansion of the universe does not just slow, it plummets. The impossible. There is a tiny, non-zero chance that the ball could suddenly find itself on the other side of the mountain without ever rolling over it. It simply teleports. In our cosmic scenario, the ball is the entire state of the universe, and the mountain is the barrier separating our near-nothingness from true nothingness. The universe could, in one random quantum fluctuation, tunnel from its current low-energy state into a state of true vacuum, a configuration where the total energy of everything, including space itself, is precisely zero. This is not empty space. This is the absence of space, time, and the very fields that define reality. It would be a transition to literal nothing. One moment, there is a vast, cold, empty cosmos. The next, there is not even emptiness. There is no there. No photons, no quantum fluctuations, no potential for anything to ever happen again. It is the ultimate fade to black, where the screen doesn't just go dark, it ceases to exist. This event would have no cause, no signal, and no witness. It would happen everywhere at once, because it is a transition of the entire universe's state. The timeline for such an event is meaningless, as time itself would end in the transition. But if we could somehow clock it, the odds are so astronomically small that the expected wait time would be a number so large it dwarfs the Google years of the black hole era. It is an end that makes even eternal heat death seem temporary, a final, quiet click as the cosmos turns itself off for good. The walls of our bubble universe may not be the only danger we face. We have already explored the threat of vacuum decay, a bubble of true vacuum spontaneously forming within our own cosmos and rewriting reality from the inside. But there is an even more unsettling possibility, one that turns our universe into a potential target. Imagine a bubble of a different vacuum state, whether lower or higher energy, that does not originate here at all. Instead, it forms in a completely separate universe, a neighboring bubble in the vast foam of the multiverse predicted by eternal inflation. Through some twist of higher dimensional geometry or a chance collision in the inflating background, this foreign bubble breaches the boundary of our own. It punctures our cosmic horizon from the outside. This is not a failure of our local stability, it is an invasion. In this scenario, our universe could be perfectly stable internally, a safe and enduring home for physics as we know it, yet still be doomed by a random act of cosmic bad luck from a realm we cannot see or comprehend. The effect, however, would be just as catastrophic as a homegrown vacuum decay. The moment the foreign bubble makes contact, a wall of transformation erupts at the point of entry. This boundary is not a physical barrier you could touch, but a front of ultimate change, where the fundamental fields that govern our reality are overwritten by the laws of the invading universe. This wall expands in all directions from the breach point at the speed of light. There is no warning because the signal of the breach itself is the wall. One moment, a distant region of space obeys our familiar rules. The next, it is gone, replaced by a new reality with alien constants and forces. Galaxies, stars, and any distant civilizations in its path would simply cease to exist in any recognizable form. Their matter would be reorganized according to new foreign physics that likely cannot support complex structures. The process is absolute and unstoppable. This idea forces a chilling perspective on the concept of a multiverse. We often think of multiple universes as offering infinite possibilities, a grand cosmic tapestry. But if bubble collisions are possible, then the multiverse is also a dangerous place, a chaotic frontier where expanding domains of different physics can clash. Are we living in a quiet, stable neighborhood? Or are we in a violent cosmic intersection, unaware of bubbles expanding toward us from beyond our observational horizon? The threat is entirely external and undetectable until it arrives. It combines the relentless expansion of eternal inflation with the absolute finality of vacuum decay, presenting an end that is not a consequence of our universe's own evolution, but a random casualty in a much larger and potentially hostile metacosmos. Our entire story could be erased by a neighbor we never knew. The laws of physics feel absolute, an unchanging rulebook for reality. But what if the rulebook itself is being slowly rewritten? This is the possibility of the big change, a cosmic finale defined not by a bang or a rip, but by a silent drift into irrelevance. Our entire existence hinges on a delicate balance of numbers, the fundamental constants, the strength of gravity, the charge of an electron, the speed of light. These are not just values we measured. They are the foundational settings of our universe. They dictate how atoms bond, how stars fuse hydrogen, and how DNA holds itself together. For decades, we assumed these constants were, well, constant, locked in place since the first moments of the Big Bang. But mounting evidence from observations of distant quasars hints at something unsettling. The fine structure constant, a number that governs the strength of electromagnetic interactions, appears to have been slightly different billions of years ago in far-off regions of space. The change is minuscule, but the implication is seismic. It suggests these cosmic settings might not be fixed. They could be evolving, slowly sliding to new values as the universe ages. Now, imagine this drift continues, not as a minor historical footnote, but as a relentless trend. Over tens of billions of years, the constants could wander. Gravity might become a fraction weaker. The nuclear forces that bind atomic nucleus might lose their grip. The mass of an electron could shift. At first, the changes are imperceptible, buried in the noise of. Some models suggest W could be very close to, but not quite less than, -1. Or perhaps phantom energy's effects are not uniform. In these alternative RIP scenarios, the end is still one of disintegration, but it is a selective demolition. The RIP might only overcome gravitational bonds above a certain scale. The immense, but relatively weak gravity holding clusters of galaxies together would be the first to fail. Those vast metropolises of stars would be flung into the void. Next, the gravitational glue of individual galaxies would give way. The Milky Way, Andromeda, and all others would be shredded into a spray of isolated star systems. But then, the RIP might stop. The stronger gravity binding a solar system, like the sun's hold on Earth, could remain intact. The even stronger forces holding a planet together or binding atoms would be untouched. The result is a universe not of total particle dissolution, but of profound, eternal isolation. Imagine our solar system completely alone, adrift in an ocean of perfect black. Every other star has vanished over the cosmic horizon, their light now forever beyond our reach. The night sky becomes utterly, permanently blank. No new stars are born, for there is no galactic gas left to collapse. The sun ages and dies on schedule, leaving any surviving planets as frozen tombs orbiting a dark remnant, sailing through an infinite void with no destination. These alternative RIPs present a different kind of horror, one not of physical annihilation, but of absolute solitude, where the universe becomes a graveyard of isolated island universes, each forever unaware of the other's existence. The difference between a total shredding and this eternal exile rests entirely on the precise value of a number we are still struggling to measure. The ultimate silence of heat death may not be empty after all. It could become a factory for the strangest form of consciousness imaginable. In a universe that exists for an eternity after reaching near total equilibrium, a profound and unsettling paradox emerges from the laws of thermodynamics themselves. Even in a state of maximum entropy, where everything is uniform and cold, quantum mechanics guarantees that tiny fluctuations still occur. Particles pop in and out of existence, creating momentary ripples in the void. Given enough time, an infinite amount of time, even the most wildly improbable event is not just possible, it becomes inevitable. This leads to a thought experiment so bizarre it challenges our very sense of reality, the concept of the Boltzmann brain. Named for the physicist Ludwig Boltzmann, who grappled with entropy in the 19th century, a Boltzmann brain is not a biological organ. It is a fully formed, conscious mind that spontaneously assembles from random quantum fluctuations in the empty space of a heat-dead cosmos. Think of it like this. In a perfectly still ocean, by pure chance, a wave could rise up that perfectly mimics the shape of a complex sculpture. A Boltzmann brain is that wave, but for consciousness. It would materialize complete with false memories of a past, a sensory illusion of a body, and a convincing perception of an entire universe around it. It would think, it would feel, it would believe itself to be a person living in a real world, only to dissolve back into the random chaos moments later. This is not science fiction, but a stark implication of physics taken to its logical extreme over infinite time. The philosophical question it raises is deeply disturbing. Which is more statistically likely? That we are ordinary beings living in the relatively low entropy early universe, the product of 13.8 billion years of orderly cosmic evolution, or that we are boltzmann brains, momentary flukes in a vast, eternal void, hallucinating all of this from scratch. In a cosmos that lasts forever, the number of these random, self-aware fluctuations would eventually dwarf the number of real, biologically evolved minds from the universe's brief, fiery youth. From this perspective, the most common form of consciousness in the ultimate future would not be housed in a body, on a planet, orbiting a star. It would be these transient, disembodied illusions, flickering into existence amidst the endless dark, each one convinced it is living a real life before vanishing without a trace. The end of the universe, in this view, is not merely cold and empty. It is ironic and surreal, a realm where the fading memory of thought outlives the stars themselves, manufactured by the random churn of a cosmos that has forgotten how to make anything else. The fear of destroying the universe is not just a science fiction trope. It is a question physicists have had to take seriously. Could our own experiments, in our quest to understand reality's deepest secrets, accidentally trigger the end of everything? The most famous candidate for such a cosmic trigger is the Large Hadron Collider, the most powerful particle accelerator ever built. It smashes protons together at velocities incredibly close to the speed of light, recreating for a fleeting instant conditions that have not existed since the first trillionth of a second after the Big Bang. In those microscopic fireballs, could we create something catastrophic? 3 theoretical monsters have been suggested. A strangelet, a hypothetical nugget of strange matter that could convert ordinary matter on contact, turning the entire Earth into a lump of exotic particles. A micro-black hole, so tiny it would evaporate instantly, according to Hawking's theory. But what if Hawking was wrong and it started to grow? Or, most chillingly, a bubble of true vacuum, the very spark of vacuum decay, the big slurp itself, nucleating right here in our detector. These are not frivolous ideas. They are based on extrapolations of our best theories. And so, scientists at CERN and around the world have conducted rigorous safety reviews. Their conclusion is a resounding and scientifically robust all clear. Here is why. First, nature has been running its own particle accelerator experiments for billions of years. Cosmic rays, particles accelerated to mind-boggling energies by distant supernovae and black holes, are constantly bombarding Earth and other celestial bodies. The most powerful of these carry energies millions of times greater than anything the Large Hadron Collider can produce. They have been colliding with the atmospheres of planets, with the surfaces of neutron stars, with the dense cores of galaxies for the entire history of the cosmos. If such collisions could create stable strangelets or persistent black holes or vacuum decay, the universe would have ended long ago or shown clear signs of such disasters. The fact that we and the stars around us still exist is powerful empirical evidence that these events are either impossible or spectacularly unlikely. Second, the safety reviews delve into the detailed physics. Any micro-black hole produced would have a mass so small it would evaporate in a fraction of a second due to quantum effects, far faster than it could gobble up any matter. The conditions needed to create a dangerous strangelet are not met in our collisions. And the energy required to kick the Higgs field into a true vacuum state is, according to our best calculations, astronomically higher than anything we can muster. The universe is not so fragile that a machine in a tunnel beneath Switzerland can undo it. Yet the very act of conducting these reviews is profoundly significant. It represents humanity, for the first time, consciously assessing whether our pursuit of knowledge could pose an existential risk to all of existence. It is a moment of profound responsibility, a check on our own power. The takeaway is not fear, but a strange kind of reassurance. The cosmos has endured far greater violence than we can ever produce. Our experiments are a whisper in a universe that has already shouted. The real danger was never in our machines, but in the unsettling revelation that the laws of physics might, in some obscure corner of theory, allow for such an end at all. That discovery in 1998 was a cosmic thunderclap. Two independent teams of astronomers observing distant supernovae expected to find the universe's expansion slowing down under the relentless pull of gravity. Instead, they found the opposite. The most distant stellar explosions were fainter than they should have been, meaning they were farther away than predicted. The expansion was not slowing, it was speeding up. This was the direct, observational proof of dark energy's dominant role, a revelation that earned the researchers the Nobel Prize in Physics. That single data point, that upward curve on a graph of the universe's expansion history, overturned centuries of assumption. It meant the big crunch, the grand collapse driven by gravity's victory, was off the table for our universe. The initial throw, forces over cosmic time. It is as if the universe's operating system is running a very, very slow background update, one that alters the core programming. The long-term implications are staggering. This is not a sudden apocalypse, but a slow-motion unmaking. If constants like the fine structure constant continue to drift, they will eventually cross critical thresholds. The delicate nuclear resonances inside stars that allow them to forge carbon, the very element of life, would vanish. Stellar furnaces would sputter and fail, leaving the universe unable to produce new, heavy elements. Chemistry itself would become impossible as the forces that bind electrons to atoms weaken, dissolving matter into a formless plasma. A universe governed by drifting constants would not end with a bang or a freeze, but with a whimper of irrelevance. It would evolve into a state where the complex structures we see today, from galaxies to DNA, are not just gone, but were never possible to begin with. The cosmos would become a simpler, poorer place, its once rich tapestry of physical law fading into a bland and sterile uniformity. The big change asks a haunting question: are we living in a cosmic golden age, a brief window in the universe's long life where the constants are, by sheer luck, perfectly tuned for complexity? And if so, how long until that window silently slides shut? Deep beneath the mountains of Japan, scientists are waiting for a single atom to die. The Super Kamiokande detector is a colossal tank holding 50,000 tons of ultra-pure water, buried a kilometer underground to shield it from cosmic interference. Lining its walls are over 13,000 golden eyes, photo-multiplier tubes waiting to catch a fleeting spark of blue light. This is the frontier of the search for proton decay, a quest to witness the bedrock of matter betray its own permanence. Every second, trillions of neutrinos from the sun pass through this silent chamber, but the researchers are watching for a different signature, the telltale flash that would signal a proton in one of those water molecules spontaneously coming apart. So far, after decades of watching, the protons have held firm. This profound silence has given us not a discovery, but a critical limit. We now know that if protons do decay, their average lifetime must be longer than 10 to the 34 years. That is a 1 followed by 34 zeros, a span so immense it makes the current age of the universe seem like a single heartbeat in a million human lifetimes. What would such a decay look like? Inside the nucleus of an atom, a proton would not explode, but quietly transform. According to many grand unified theories, it could break down into a positron, the antimatter counterpart of an electron, and a neutral pion, a particle that would immediately decay into 2 high-energy photons of light. It is a silent, quantum-scale metamorphosis, where the heart of matter becomes a whisper of radiation. Now, project this rare event across the cosmic dark ages of the far, far future. The last stars are cold iron cinders, black holes are the only landmarks, and the universe is a near-perfect vacuum at a temperature just above absolute zero. In this profound stillness, the invisible clock inside every remaining piece of matter finally ticks down. Consider the corpse of a star like our Sun, cooled over eons into a crystalline sphere of carbon, a planet-sized diamond. It is the ultimate symbol of permanence, harder than any material we know. Yet even this diamond mountain is not eternal. Proton by proton, atom by atom, its substance undergoes a slow, inevitable sublimation. The strong nuclear force that held its atomic nuclei together for trillions of years is not absolute. Over these inconceivable spans, the solid crystal does not crumble, it radiates. It glows with a faint, cold light as its very mass leaks away into positrons and gamma rays. This is the granular, material end of everything tangible. Every asteroid, every frozen planet, every dark star remnant will eventually dissolve into a diffuse mist of fundamental particles and light. This process is not a dramatic event, but the universe's final act of forgetting what matter was. It is a key, grindingly slow chapter in the larger story of heat death, transforming a graveyard of cold objects into a featureless, ultra-thin soup where even the memory of structure is lost. The enduring silence of detectors like Super Kamiokande tells us this fate is not imminent, but it also hints that the universe has provided, in its fundamental laws, a recipe for its own ultimate dissolution, one proton at a time. The profound silence of our proton decay experiments speaks to a universe built to last, but even its most permanent structures are not eternal. In the far future, long after the last stars have faded, the cosmos enters its most dominant and patient phase, the black hole era. For trillions upon trillions of years, these gravitational titans will be the sole rulers of a dark universe, the final monuments to a vanished age of light. Yet, a quiet revolution in physics has revealed their reign will not be forever. Stephen Hawking's most famous insight showed that black holes are not perfectly black. They glow, they shrink, and they ultimately vanish. The key lies in a bizarre marriage of gravity and quantum mechanics at the very edge of reality, the event horizon. According to quantum theory, empty space is not truly empty. It is a seething sea of virtual particles, pairs of matter and antimatter that constantly pop into existence and then annihilate each other almost instantly. This is happening everywhere, all the time. Normally, these fleeting pairs vanish without a trace. But at the precipice of a black hole, the immense gravitational pull can intervene. Imagine a particle-antiparticle pair flickering into being right at the event horizon, the point of no return. In a stroke of cosmic bad luck, one particle falls in while its partner escapes into the void. From the outside, it appears the black hole has emitted a particle. To conserve energy, the particle that fell in must have negative energy relative to the outside universe. This reduces the total mass, and therefore the gravitational pull, of the black hole itself. It is a slow quantum leak. This is Hawking radiation, a faint thermal glow whose temperature is inversely related to the black hole's size. A massive black hole is incredibly cold, emitting barely a whisper. But as it loses mass, it shrinks, and as it shrinks, it gets hotter, radiating away its remaining mass faster and faster. The process is unimaginably slow for a stellar mass black hole, taking around 10 to the 67 years, but it is relentless. The final moments are anything but slow. As the black hole approaches microscopic size, its temperature soars. The faint whisper becomes a shriek. In a final, violent flash, the remaining mass converts into a burst of high-energy particles and gamma rays. A black hole with the mass of a mountain would explode with the energy of 1,000,000 1-megaton hydrogen bombs. And then, it is simply gone. This evaporation poses one of the deepest puzzles in modern physics, the black hole information paradox. Quantum mechanics states that information about what falls into a system can never be truly destroyed. But if a black hole evaporates completely into random thermal radiation, What happened to the detailed information about every star, planet, or book that ever crossed its horizon? Was it scrambled beyond recovery, or is it somehow preserved in the final burst? The answer could rewrite our understanding of reality. This slow-motion evaporation defines the middle chapters of nearly every cosmic endgame. In the heat-death scenario, it is the penultimate act, clearing the stage for the final, particle-less dark era. In a bouncing universe, it might be the prelude to a new beginning. For billions of years, these dark beacons will be the only landmarks in an expanding void, their patient glow the last source of heat in a cooling cosmos, until quantum mechanics calls in its final debt and each one winks out in a silent, brilliant flash. The Higgs boson is more than a particle, it is the architect of mass, and it may also hold the blueprint for our universe's ultimate stability, or lack thereof. That famous discovery at the Large Hadron Collider did more than confirm a theory. It gave us a precise number, the mass of the Higgs. This number, combined with the mass of another heavyweight particle, the top quark, allows physicists to calculate the shape of the Higgs field's potential energy. Think of this potential as a landscape of valleys and hills. The depth and shape of the valley our universe currently sits in determines everything. If the valley is deep and steep, we are in a stable, true vacuum, safe for eternity. If the valley is shallow, we are in a false vacuum, a precarious perch. The calculations using the measured masses point toward a startling possibility. Our cosmic valley appears to be shallow. We are not sitting at the very bottom, but in a local dip on the side of a much deeper, far more stable chasm. This is the metastable state. It is like a ball, carefully balanced in a small hollow on a mountainside. It feels stable, it can stay there for an incredibly long time, but a strong enough nudge could send it rolling down into the true minimum far below. That nudge could be a rare, high-energy quantum fluctuation, or an immensely powerful cosmic event. The moment the Higgs field tumbles into that deeper valley, it triggers vacuum decay. The new, lower energy configuration of the field would spread at light speed, rewriting the laws of physics in its wake. The unsettling takeaway from our most advanced experiments is that our entire universe might not be in its most comfortable permanent state. It might be in a state of cosmic suspense, a temporary arrangement that has, through sheer luck, persisted for 13.8 billion years. The very particle that gives substance to our world could be the key to its sudden and total erasure. But the dangers lurking in a multiverse extend far beyond the walls of colliding bubbles. If our cosmos is one of countless others, then our local laws of physics are not universal decrees, but merely the bylaws of our particular neighborhood. This opens the door to endings that are not just destructive, but bizarrely alien. Consider the cosmic fossil. In the chaotic froth of eternal inflation, different bubbles may have crystallized from the inflating background at different times and under different conditions. Some might have experienced phase transitions early in their history, moments when the fundamental forces split from one another. Such transitions can leave behind topological defects, frozen scars in the fabric of space. A cosmic string is a hypothetical remnant, an infinitely long, unimaginably thin filament of concentrated energy, thinner than an atom, but with the mass of a mountain range per inch. A domain wall is a two-dimensional sheet of pure energy, separating regions of space with different physical properties. These objects would be relics from a more violent, early universe. But in a multiverse, they might not be confined to their own bubble. Through some higher dimensional loophole or chance intersection, a cosmic string or domain wall from a neighboring universe could, in theory, pierce into our own. The moment it breaches our space, the effect would be catastrophic and instantaneous. A cosmic string slicing through a planet would cut through it like a wire through cheese, its immense gravity causing devastating earthquakes and tidal forces long before contact. A domain wall sweeping through the solar system would be a curtain of annihilation. As it passed, the laws of physics on one side could be different from those on the other. Matter might simply cease to function as it crossed this boundary, unraveling into energy or reconstituting into an alien form. These are not explosions, but incisions and erasures performed by artifacts from a universe with a completely different history. And then there is the grandest, most speculative ending of all. If our bubble universe can decay from a false vacuum to a true one, could the same be true for the entire multiverse? The inflating background, the vast ocean in which our bubble floats, might itself be sitting in a metastable state. A single quantum event in that primordial sea could nucleate a bubble of a deeper, more stable vacuum that would then expand at light speed, not just through one universe, but through the entire multiversal landscape. It would be the big slurp on the ultimate scale, a wave of true nothingness that consumes not just our reality, but every possible reality, rewriting the meta-laws that allow bubbles to form in the first place. In this vision, every cosmos, every history, every possible version of you and me would be simultaneously erased, replaced by a single, uniform, and likely lifeless state. This is the limit of our speculation, a final curtain call for all of existence. It reminds us that if the multiverse is real, then the list of potential endings is not just long, it is virtually infinite, bounded only by the wild frontiers of theoretical physics and our own imagination. Our story becomes one fragile narrative in a library of infinite tales, and that library itself may have a closing time none of its stories can foresee. 24 endings, each a masterfully crafted tale of cosmic destiny, and yet the final word on our universe's fate remains unwritten. We have journeyed through the cold silence of heat death, the fiery collapse of the Big Crunch, the violent shredding of the Big Rip, and the silent erasure of vacuum decay. We have considered proton decay, black hole evaporation, brain collisions, and drifting constants. But all of these scenarios, as varied and dramatic as they are, share one fundamental limitation. They are built upon the twin pillars of modern physics, general relativity, and quantum mechanics, frameworks that work spectacularly in their own domains, but become incompatible at the extremes. The singularity of a black hole, the first instant of the Big Bang. These are places where our equations break down, spitting out infinities. This means every single prediction we have explored is, in a profound sense, provisional. They are the best stories we can tell with an incomplete script. The true finale, the ultimate way the universe could end, is the one we cannot yet conceive. It is the surprise ending written by a theory of everything, a complete unification of gravity with the quantum world. Such a theory would not just tweak our predictions, it could revolutionize them entirely. It might reveal that our cherished concepts of space and time are emergent illusions, mere shadows of a deeper reality. In that,